Hmm? Oh, you got some other, huh? Oh, you cannot sign in? Oh, use a mobile device or go to Los Rios password reset. Search for that. Oh, you don't? Ouch. Okay. Yeah, yeah. All right. So we're gonna get the lecture started today. Um, So I'm going to focus on the lab first. Okay, so your lab today is params and return value. So we're going to focus on that one. It's a repetition of the topics that we have already talked about in this class. So we actually cover all of that material already. Um, so instead of covering the same thing over and over again, I think I'm going to start with a new program, or you guys can come up with a program and you can ask me how it is going to be implemented in assembly language. So how do you guys want to proceed? Absolutely. Well, I mean, I only do C and not C++, so no object-oriented code. But other than that, yes. So do you want to kind of write it on the whiteboard, or how do you want me to get the program that you want to examine? You can type on my keyboard. I mean, I can give you this. All right. So go ahead. You can type it. All right. It's all yours. This is the professor's version of lead code. So yeah, go ahead and type whatever you want, and then I'll make some adjustments. Well, because everything is still being recorded, I'm just going to use this opportunity also to share why internships are important. Um, because I think the ratio of interns being actually hired later on is actually quite high. According to the people from yesterday, it's about 90% with the internship program at HP Enterprise in Roseville. Now, do other companies have the same ratio? I do not know. Okay, but HP Enterprise seems to have a pretty high ratio of actually hiring their previous interns as full-time employees. And one of the students asked, um, so why would a company not hire an intern, from an internship? The answer was actually pretty clear. I did not even understand why the question was asked. It's because the internship showed the company how this person would not be a suitable employee. um, so that was kind of funny. Um, And for the most part, depending on the company, internship programs tend to also train the employees. So you don't have to go in as an intern to be like superior in every possible way. You go in, you may not even have, some of the soft skills that they're looking for, like, team working and stuff like that. They, as an internship program, they have team building activities. They have people coming in and talk about how to team work together, how to work with other people, and so on. So if you can get into an internship program, get into one. Okay, especially a paid internship with a relatively large organization like HP Enterprise, or Wells Fargo if they have an internship program. IBM is a great one if they have an internship program too. But look for internship programs. Yeah, go ahead. They're just internship programs. Yep. Yeah, they don't compensate really well, so you're not exactly paying, you're getting paid the same amount as a real software engineer. I would take anything. I would take anything that relates to computer science in any way, software development or computer architecture, because if they accept you as an intern, they think that you have the potential. So you don't have to worry about that part. Just apply. If they accept you, you're good. Yes. And most of the time, companies don't expect interns to know the technical stuff already. They're really trying to use the internship itself to assess how quickly you can learn and how quickly you can apply what you have learned. So that's why, it's a great opportunity not only to potentially get an employment later, but it's also like taking classes, except you're getting paid. So definitely, look into that. All right. So the question here is not something that is related too much to this class because this has to do with what we call overloading. That's right. So it's overloading a function because you have the same function name. So you can have the same function name, even that will work. Because what the compiler does is it recognizes what arguments you're using. So in this one, it will first notice that you're using a float for the first argument, and it will try to make a best match of which function to actually use. So, but it's not something that relates to assembly language programming because the implementation of both of these would be about the same. So how we use the stack, how we use the stack for passing arguments and returning the result would be the same. TTP has no ability to deal with floats, so we can't really do that, with text toy processor because that it's so simple. It cannot handle floats. Yep. Um, Quite a bit, okay, because Logisim does not actually have um, units that can handle floats. So that means I would have to build that from scratch. So I would have to handle addition, subtraction, at least, in using floats, and that's not going to be easy. Um, if you look at the actual processor die, the FPUs, floating point units, compared to the ALUs, the FPUs are much larger in terms of die size. They use up a lot of transistors. So that's why the TTP has no floating point capability. All right. So I'm sorry. So this is not something that is directly something that I can address. However, based on the inspiration from my CISP 300 class, we can talk about things that are related. Okay. So we'll go back and use like a regular sum. Okay. So we'll do a pound include standard integer.h. So I want to make this program compilable so that you can actually compile and run it through GDB if you want to. So this part is about the same as what we talked about the other day. U in 8 underscore T. Sorry, that's me not thinking through. There we go. X, Y. And all it's going to do is to return X plus Y, like so. And now we are going to throw in two additional functions, maybe. Okay. So I'm going to throw in the same function in my CISP 300 class. The first one is called Johnny, and Johnny is going to return 5. The second one is Ryan. It's going to return a 7. And then we get to main, int main. And this int main is going to do something really funky. It will call sum, and then the first argument to sum is the return value of Johnny, and then the second one is the return value of Ryan. And it's not going to do anything about sum itself. Okay, and then we have a return 0. Okay. So this program looks completely silly because there's not a single local variable here to store anything, right? And yet we have 3 functions all returning specific values, okay? So now we go like, okay, this program probably won't even compile, okay? We'll see. So what I'll do, because I was trying to use online GDB earlier and it was kind of a nightmare. So I'm just going to use my command line interface here to compile and run the program. So we'll go ahead and cat this program to, okay, we'll call it 12.c. Okay. Okay, nothing, no one says I cannot use, just digits to name a file. Okay, so it's actually perfectly legit. Okay, it's perfectly legit. And Ryan's supposed to be returning 7, not 8. Okay, because otherwise it'll be returning 13. So we'll go ahead and fix it. All right. So if anyone is interested in why I name the functions like this, um, Johnny is from a movie called Short Circuit. Okay, and in that movie, Johnny is number 5 as a robot. So number 5 was his original designation, as a robot, but people call him Johnny. So Johnny 5 is alive is a kind of famous line from that particular movie. Ryan and Seven, they're related because the character of Seven of Nine in Star Trek Voyager, the actress's name is Jerry Ryan. So that's why Seven and Ryan are also related. Okay, so people who don't understand the sci-fi reference will always ask us like, why do you name these things, five, Johnny and Ryan, and why 5 and 7? So that's kind of the relationship between those two. All right, so now that we have a program like this, we'll go ahead and see how it runs in C++ first, like on a regular computer. So we'll go ahead and compile the program, GCC -G, which means I want to use the debugger, so include all the symbol table, -O, which means I'm now naming the executable, and then we give it the source file, and now it compiles. Everything looks good. GDB 12, okay, 12 is the executable. So now we can use L to list the program. So we're gonna stop at line 13. Okay, so we'll put a breakpoint on line 13, which is right after the call to sum, which does not seem to leave a trail of anything behind because the return value was not stored anywhere, right? So what is the one thing that you learned from Monday that talks about the side effect of a function that returns a value? How is the return value, which is a scalar in this case, returned? A register. Yep. In fact, register A, right? It is A register, which is also register A. Okay. As it turns out, it is the same thing in GDB. In the Intel architecture, it is also register A, except it is the 64-bit version of register A. When we use AMD 64 as the instruction set, so that one is called RAX. Okay, it's a naming convention thing. And guess what it is? Okay, this is the side effect. Okay, so now the question is, okay, so how do we actually write the code corresponding to line 12? Okay, because the function calls Johnny and Brian, those are super easy, but line 12, how do we figure out, how do we handle line 12 in assembly language? So that's the question. Okay, is that okay? Does everybody understand, what I'm about to illustrate? Yes, go ahead. Hmm? Okay. So we'll go get the functions implemented first because that's the easy part, and then we'll get main implemented as the second part. Okay, but before we go there, I just want to make sure that the C program itself does not present a question. So let me go back to the C program and make sure that we are all good with the program itself. Do we have any questions about the C program itself? Nope. Okay, we're all good. Okay. All right, so with that said, we are going to do the usual thing, okay, which means I'm going to make a copy of this code to the TTP ASM version, and then we go to the TTP ASM version, and then we just insert, slash slash, oops, replace the starting point with slash slash with a space. There we go. And then we will start to implement everything. So at this point, I'm going to start to treat main as a regular function. Okay, so we're going to call main from the entry point code. So what we see here on line one, that's the entry point code, which means every time you start up Logisim, that's where it starts. Okay, so that's the entry point code. And then the entry point code is going to do the usual thing, pretend to initialize the stack pointer because the stack pointer always starts with 0 to begin with anyway. But it doesn't hurt to quote unquote reinitialize it to the proper value. So that's always good to have. And then from what we learned the other day, I'm going to use a different way to load the return address now. Okay, so LDI register A with dot 6 plus in this case. Um, and I'll explain that. Okay, give me a second. I'll explain that. Dot 6 plus, and then we do a push, which means we have a decrement D, stda, and then we continue to jump to main because that's how we call. When main returns, it will get to the halt instruction, and we'll even try to make a shell out of main. So main is just a shell. I'm not going to implement anything inside except for the return. So it's going to LDIA with a 0, because it's returning a value of 0, and then we're going to go back to the caller. So to go back to the caller, it's the same thing, LDBD, okay? We retrieve the return address, and then we increment D, okay, because we need to deallocate the return address, and then do a JMPB. Okay, there we go. So at this point, okay, I think from line 24 to line 26, we should have a pretty good recognition of what that is. Okay, it pops the return address, and then we continue execution according to the return address. Question? Nope, we are good. All right. And then line 23 is just return 0, okay? Because we are putting the value of 0 into register A because according to the caller callee agreement, the return value, especially in the case of a scalar, is supposed to be in register A. So are we good so far? Okay, so the only mystery of this entire program at this point is line 3, okay? So we go like, okay, what are we actually putting into register A on line 3? So the first question is, what does the dot mean? The dot means the address of the opcode on the same line. In other words, this dot is representing the address of the second LDI instruction, which is on line 3. Are we good with that? No? That's just the syntax, okay? That's really it's just the syntax of the assembly programming language. So whatever this LDI opcode is represented by the dot here. Are we doing okay? All right. Hmm? Putting in. Okay, let's not do the 6 plus. So I'm going to comment out the 6 plus for now. And we'll just assemble the program because it's not going to run. Okay, as it is, it's not going to run. So we'll just go ahead and assemble the program so that you guys can see what is actually being loaded into register A. Is that okay? Okay, so let's do that. And I'm going to start a new shell over here so that I can keep one in the editor and the other one um, uh, in the tool folder. Okay, so nope, it's the other way around. Documents, CISP 310, River Spider. So this would be a good time for you guys to start to look into installing River Spider on your own computer. The instructions are already online. Okay, you guys can try to follow the instruction. If it doesn't work for whatever reason, I can take a look in the lab, especially. All right, so we're gonna go 12.ttp asm. We just need to get the program assembled, but might as well just use the tool because we're gonna use the tool a lot today just to trace it. And it doesn't really make things slower either. So the code is good. That's all I need for now because I just need to look at the assembled code. So there we go. And our focus is really just the assembled tab for the time being. So now we look at this instruction, and you can see how it is loading 03 into register A, and 03 itself is the address of the opcode. So that's what I mean by the dot is representing the opcode of the same line. So is that okay? Are we doing okay so far? Okay. So the dot is representing this 0, 3, and that's why, when we specify the dot to be the immediate value is just 3 itself. Are we good? It is the address of the opcode of the same line. This is the opcode. This is the address of the opcode. The dot is just that. Is that okay? All right. Okay. So if 0, 3 is the dot, then what is dot 6 plus? Now remember, this is postfix notation. So in postfix notation, dot 6 plus is really the same thing as dot plus 6 in infix notation. Okay. So what is 3 plus 6 in hexadecimal? Now, whether it's in hexadecimal or not doesn't even matter because it's just 9, right? Okay, so what is at location 9? The halt instruction. Ooh, okay. So .6 plus does specify the correct return address. Okay, but how does that work? It has to do with counting. Okay, it really is just counting. This is the dot. Okay, and we'll call this dot plus 0. Okay, because anything plus 0 is just whatever we start off with. So this is dot plus 0, dot plus 1, plus 2, plus 3, plus 4, plus 5. Guess what? Plus 6. Okay, so we are using a relative way to figure out where the return is or where the return address is compared to the LDI instruction that is supposed to put the return address into register A in this case. Is that okay? So, and that really answers the question of the last question in the lab of Monday, if you remember that question. It basically uses the same method that we are kind of talking about here. All right. So now we can go back to the source code and go like, oh, okay, so all this does, okay, once I uncomment this, is to load the return address, to register A. It's just a handy way to do that. Now, why is this way more handy and why is it better? There are two reasons. One, I don't need a label anymore because normally I need a label to indicate the location that I need to return to, like something like this, right? And then instead of using .6 plus, I would use return address 1. So what is the problem of this approach? It's not so much of a problem, it is a inconvenience because every time you need to call, you need a label to mark the return address. The second problem is what if you use the wrong return address? You use a label that is already existing, it's just a wrong label. Your program will just go to the wrong place. The function code is fine, but it will return to the wrong place. You cannot imagine how difficult those programs are to debug because the function code is fine, and then when it returns, somehow it goes to the wrong place, and then you just go like, why is it doing this? Because you specified the wrong address to begin with. No, if you use similar label names like return one, return address two, return address three, and then you copy and paste your code quite a bit, and then you forget to change some of those, then you might end up going to the wrong place because you're pushing the wrong label. You're using the wrong label as the return address. Okay? But using the other method, which is this one here, you're not going to you don't have labels. Okay, as long as you remember this template of code, it's always going to work. Okay, so this is a big plus. All right, so now that the program is fixed to the point where it will call main and return back to the halt instruction, we want to make sure that it works the way that it's supposed to before we move any further. So what we'll do is we're just going to run the code. Okay, so we'll run the code, make sure the trace looks good this time because otherwise I have to fix this first. All right, so we go back here. This time we go to the analysis tab, okay? And all we need to do is to go to the end. It goes like, okay, we did end up at location 09 on line 7. It's our halt instruction. We're all good, okay? So if you're using GitHub to track your program so that you can kind of use that to help with your interview process, this would be a good time to check in, okay? in GitHub or using the command line or using the web interface, checking your program so that you say, okay, I have a good starting point. It calls main returns without a problem, everything is good. Okay, so now we can start to focus on main. Okay, so well, actually, we can do quite a few things. So we go back to the program and then we implement all those easier functions like Johnny. Okay, so Johnny is just going to be Johnny as an entry point. It has no parameters, so we don't have to worry anything about parameters. All it needs to do is to load a with the value that we're supposed to return, which is 5, and then proceed with the actual sequence of instructions to do the returning, which is ld. I'm going to pick register D this time. Okay, there's no need to use register B all the time. Sometimes you can use B, sometimes you can use C. Increment D, JMP C. So the only thing that needs to be consistent is on line 19 and also on line 17, you use the same registers. You have a choice of B or C. A is not available because register A is serving a special purpose in this case. Register D is also out because your register D is the stack pointer. Can't use that one either. All right, so this is Johnny, and then we'll go with Ryan. Okay, so that's going to be similar or very, very similar. Okay, it's just the value being returned is a 7 instead of a 5. Okay, so now we look at this code and go like, feeling pretty good about it. Say again? I need a label. Oh, right, the entry point label, Ryan. There we go. Ryan, thank you. Okay, so these two are not really too difficult, but if you want to debug these two, okay, we can debug those because we have to call them eventually anyway. So might as well just kind of, okay, let's double check that we can do that. So over here, we're going to call Johnny and then we'll call Ryan. Okay. In fact, we'll call Ryan first for one interesting reason. Okay, so there we go. So we say call Ryan, which is LDI. So we're going to use our newfound best sequence to call. Okay, do this decrement D, STDA, JMPI to Ryan. And then when it resumes, it'll be at this point, there's nothing to clean up this time because calling Ryan does not require any arguments. And as a result, there's nothing to clean up. And then we'll go ahead and call Johnny too, just to be sure. Okay, so we'll basically repeat the 4 lines of code and then paste it here. And this time we're going to call Johnny, Johnny. There we go. All right. So now we try to make sure the code is still working, okay? And in between, we want to identify that by the time we get to line 37, register A should have a value of, this is right after we return from Ryan, a call to Ryan. So it should be 7, and then by the time we get to 44, register A should be 5, right? Okay, so we'll kind of keep track of that, and then save the program, and then just kind of run it again. But this is how I would envision people to write code for this class is not to write a whole lot of code. Okay, you write a little bit, you double check it, make sure it works the way that it's supposed to, and then you write a little bit more if it works out. So now we go back to the trace, okay, and let me go back to the line number first. So we are expecting register A to be a 7 by the time we get to line 37. So I like this trace because column F are the line numbers. So you can go to line number 37, and then you ask, okay, what was the last time we update register A? Oh, this is right where we update register A the last time. So by the time we get to line 37, register A is going to have a value of 07. Okay, that's how we know that. And then you can go to the other one, which is on line 44. So now we track down line 44 in column F, which is right here. And then you ask, what was the last time we update register A? This is the last time we update register A. So by the time we get to line 44, register A is going to have a value of 05. So we're all good there. Okay. So now we go back to the source code and then we ask, okay, we know how to handle the call to Ryan by itself. We know how to handle the call to Johnny by itself. So how do we use the return value of Ryan and also the return value of Johnny as arguments when we call sum? Yes, push the return values, right? But they're all in register A, right? So that means, oh, okay, so by this time I would have the return value of Ryan in register A, just need to push it on the stack. So that would be pretty easy. Okay, this is how we push stuff on the stack, like so. And this is also how we push stuff on the stack. So that means by the time we get to line 45, whatever instruction is over there, we should have 7 at the highest address because that's where we have to push the last argument first. And then by the time we get to yeah, so by the time we get to line 39, we should have 7 pushed. By the time we get to line 45, we should have 7 and 5 also pushed. So we want to double check that, right? So we want to double check this and we put a halt instruction here. So this is also a really nifty trick of double checking that your code is working the way it's supposed to up to a certain point. Because I'm not done with this code, but I'm trying to make sure that I have the arguments all set up correctly before I call sum. So um, make sure I save the code and then go back to trace it again. Okay, so we trace again. Da, 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 da. But at the same time, it would be a good time to kind of figure out what is supposed to be on the stack. So as Logisim is doing this, or if when the script is doing this, I am going to start a new spreadsheet for today so that we can actually look at how the memory is supposed to look like. And we can put it into this folder. Okay, so new Google Sheets, and then name it after today's date, 2025, 10/29. Okay, there we go. And I'm going to use this for location 255, 254, 253, 252, and so on. Now, if you want to have a column to reflect the actual hexadecimal number, you can use this one. There's a particular formula that is really useful. It is called dec to hex, decimal to hexadecimal. And you just have to kind of put it cell over here, and then you can now drag it down a little bit like so. Now you have the hexadecimal representation of those locations. This location was used to return to the entry point code. So we'll just go like, okay, this is the return address to the entry point code. This is going to be the 7, and this is going to be the 5. So the 7 would be parameter y, param y of sum. This would be param x of sum. The next one is going to be the return address back to main. Okay, so this is the kind of stuff that we're expecting on the stack. Okay, and now I'm pretty sure the assembler, I mean the trace is all done. So now we look at the overriding of RAM locations. So the first RAM location override is over here. This is the return address to the halt instruction. So that means we have just accounted for this part here. Okay, I'm gonna close up the other one because they are not useful for today. So we'll go ahead and close those. All right, so the next override of RAM location is this location. This is in hexadecimal. So now the question is this a 1A? That doesn't seem right to me. Am I looking at the right code? Okay, did I make a mistake? Oh, that's the return address to Ryan. Okay, so we're still good. We're still good. The same location was reused later. Okay, so let me explain. Um, the first time we wrote something over to location FE was the return address when we need to call Ryan. Okay, so that's why that location was used first. And then later on, we rewrote that location after we returned from Ryan to save the return value of Ryan. So those are the two separate writes to the same location. Are we good with that? Okay. And then the same thing happens to the next location. This is the return address of calling Johnny, and then this is the actual return value of Johnny. So at this point of time, the stack should look exactly like the way we predicted up to this point. Are we good? Okay. So now we are ready to deal with the function called sum. So now we go back to sum, and then we try to implement it. So this is sum. Okay, sum has an entry point of sum. And the way I like to do it, is to take a look at what is on the stack. We have parameter y pushed first, then we have parameter x pushed second, and then we have the return address pushed last from the perspective of the caller, which is also where the stack point is going to be pointing to. So that means x is going to be at 1 byte offset from where the stack pointer points to. Y is going to be at 2 bytes from where the stack pointer points to. So I just want to make sure that on lines 12 to 14, we understand what that is representing. We good with that? Okay. So obviously, with this one, you can probably remember all the offsets and not need to create labels. But personally, I like labels. So I have a very systematic way to look at LVS first, local variable size, none of those. Put a 0 here, and then sum underscore x, which is my first parameter, is going to be sum LVS 1 plus. This one here has to account for the return address. That's why we have a 1 here. And then we have sum underscore 2, which is sum underscore x1 plus, because it is 1 byte after that. So this is the way I do it. Now, when you write your code, do you have to do it the same way? The answer is no, okay? But somehow you have to track everything in a very consistent way. So it's up to you to decide how you want to deal with that. All right, so since we don't have any local variables, I don't really have to allocate. I don't need the code to allocate anything. So I can start off with, I usually start off with the return code so I don't forget. So LD, BD, increment D, JMPB. Okay, I just, get that done so I don't have to go back and worry about, oh, did I write the return code? Yep, it's always going to be there. So now I can go ahead and try to access, X and Y, okay, because I need to add those two, okay, because what we are trying to do is to implement the return code here. Okay, this is what we want to implement. So we need to do LDI, pick one of the three registers, A, B, or C. We'll pick one. We'll pick A. And this is sum underscore X. Now, this is the offset to find parameter X from where the stack pointer points to. So to get to the address of parameter X, you have to add the stack pointer, and that would only get you the address of X, not the value of X. So you need an LDAA in order to get to the actual value of X. So we could do the same thing with Y. Okay, LDIB sum Y, add BD, LDBB. So now the value of X is in register A, the value of Y is in register B. I just need to add AB so that the sum is automatically stored back into register A, which is where I want it, and sum is done. Okay, so at this point, where do I stick a call to sum? Just kind of scroll down here. We got Johnny done, we got Ryan done at this point. So the call to sum is going to be here. So I just need to do LDI A 1A comma dot 6 plus. It is just a call, right? So we have to load the return address, decrement the stack pointer, stda, which is part of the push operation. And then this time we do a jmpi to sum. Now, when sum returns, we have to be careful because sum has two arguments. They're both on the stack right now. But by the time we get to line 73, I don't need those arguments anymore because sum is already done. The invocation is done already. So that means I have to be, as the caller, I'm the only person who knows how many bytes to deallocate. So I have to deallocate in this case 2 bytes, which would be the value of 7 on the stack and the value of 5 on the stack. All right. So by this time, okay, by the time we get to line 78 this time, register A should have a value of 12, not 5. It is 12. because we actually did the sum thing. Hmm? I added the two arguments. So for each call, okay, for every single call, the return value is in register A. So these two instructions are the important ones because they push that return value on the stack. Because otherwise, the next LDIA is going to destroy the return value. We good so far? Okay. So by the time we get to line 62, register A, um, mm, I take it back. Okay. So by the time we get to line 59, okay, register A is going to have the return value of Ryan, which is 7. The next instruction is decrement D, doesn't change the value of A. STDA does not change the value of A, but this will change the value of register A, right? So that's why these two instructions, they have to be before this instruction. We have to save the return value of calling Ryan before we use register A for something else and overwrite the value of register A. Does that make sense? Okay, so we're gonna run this code and see if we get 12 back at this point over here. So by the time we get to line 73, register A should have a value of 12, which is 0C in hexadecimal. So we save the code and then we run it again, and then we'll see if that is the case. Okay, so now we go back to the trace, which is in the assembler, and then we look at, okay, I have to remember the line number. The line number is 73, so we just look up line 73 in column F. Okay, 73. All right, this is 73. The last time we update register A, it was with a 0C, so the program did correctly store 12 into register A as the result of the function call. So are we doing okay so far with this program? How we use two function calls to supply arguments to yet another function call. Yes, we are at A and D. At AD. Okay, I'm not sure which line this is. Okay, maybe it's better here. Hmm? In the sum function. Okay. Yes. Okay. Well, to answer the question, the first question is what did we do on line 21? Go ahead. So it had. Hmm. It's actually a little simpler than that. So the first thing is we need to look at how the stack or how the frame looks like. So this is the call frame of sum at the entry point of the function. The stack pointer is expected to point to the return address. One byte after that would be the value of the first parameter, which we know as x, And then 2 bytes after where the stack pointer points to is where we can find parameter y. So is this part understood? Okay. So accordingly, I would use these label definitions. So label sum x really is just 1, sum y is really just 2. Is that okay? So now we put sum x, which is 1, into register A. But the idea is I need to find out where x really is. 1 is not where it is. It is 1 byte from where the stack pointer points to. So how do I get to the address of x when all I have in register A is the offset of where to find x from where the stack pointer points to? You add the stack pointer to it. You add the stack pointer to 1, not the other way around, because you don't want to destroy or modify the stack pointer. So you add the stack pointer to the offset so that the offset now becomes the address of x. Yep, yep. hmm Now, so this part, when if you really want to take a closer look at how this works, you just look up the line number, which is line 21, and then you go to the trace and you look up line 21 in the trace. So you just look up line 21, which, oh, we just got past it right here. So you can see how register A start off with a value of 0, 1, and the stack pointer is a FC. So FC plus 0, 1 is FD. And then we look up the stack setup and we can see that, oh, okay, FD is really the address of parameter x of sum, which has a value of 5. So these things all kind of go hand in hand, um, which reminds me to mention that it's always a good idea to take a snapshot of this, okay? And then once you have a snapshot of this, when I say a snapshot, I don't mean a screen snapshot. I mean go here, go to File, and then go to Make a Copy. Because once you make a copy, your copy is decoupled from the one that I'm using. Then you can go ahead and annotate all of these lines any way you want. So this way, the explanation that I just did, you can put it into the cell and explain what is going on with this line, what is going on with this line, and what is going on with this line related to the C concepts. I believe on Monday I did some commenting, right? So you might want to gonna rewatch that video because I think on Monday I did something like this. A is now the address of x minus the stack pointer because it is relative to the stack pointer. I believe I did that on Monday. Yes? Okay. So I'm not going to do it today. You will hear this from me many times, and many people will find it annoying, and that's why I do it, which is I am not commenting the program so that you can do it. Okay? It's not like I don't explain it, I just don't write it down. So this way, when you rewatch the video, you can do your own annotation because that way it would sink in a little bit better. Okay? And I know it annoys a lot of people. Well, trust me, this is nothing compared to what you have to deal with when you're employed. The kind of difficult stuff that you have to do when you're employed is nothing compared to what you have to do just by going like, okay, I have to watch the video again and go back and annotate the code according to what text said in the class. And it's all on YouTube. I'm suspecting, okay, this is just my suspicion. I'm suspecting if you download a transcript of the video and put it into ChatGPT, you upload this program to ChatGPT, you go like, ChatGPT, can you comment text code according to what he said in the class? It might be able to do that, which to you is going to be, at first, it's like, woohoo, this is easy. I can just use ChatGPT to do it. And then 5 minutes later, you suddenly feel this kind of dreadful feeling. It's like, shit, ChatGPT can do this already. What is my value to my employer? How do I get hired? That would be a very natural and logical reaction, I'm gonna have to say. I'm afraid that is a natural and the logical reaction to being able to do all this stuff in ChatGPT. All right. So, any questions about this? No. All right. So we're going to change the program a little bit and make it a little bit more interesting. Okay. And this time it's a little tricky, I have to say, but it's not so much so tricky that it is not something that we cannot handle. So we'll go ahead and get out of this one, and we'll go like, mm, I'm just thinking, how to formulate, how to call the name of the program. Mm, I'll just call it test. I'm running out of ideas to how to call the name, call the program. Okay, so this one is similar to the other one. Okay, pound includes standard integer.h. We have sum again. Okay, exactly the same way as before. In u int 8 underscore t sum u int 8 underscore t x u int 8 underscore t y return x plus y. Okay, same stuff. Okay, so this way I can actually copy and paste the implementation of sum. Okay, so this is not where things get interesting. This, on the other hand, is where things get interesting. I have a local variable. We'll call that x. Okay, x starts with a particular value. We'll call that 6. Okay, and then we're going to call sum. Okay, we'll call sum, and we'll use x plus 1 over here, x plus 2 over here, and that's all we do. Okay, and if you want to, we can store everything back to sum if you want. I mean, that's all good. All right, so this program is not complicated, right? So the first time when we call sum, x had a value of 6. 6 plus 1 is a 7. 6 plus 2 is an 8. So we are really passing the values of 7 and 8 to sum. Sum is going to add them up to 15. 15 returns. We store the 15 back into x, and that's the end of the program. Okay? So not exactly rocket science with this one. And we'll even double check to make sure that this program that works the way that it's supposed to. So we'll go ahead and gcc-g-o test.c gdb test, list the program, put a breakpoint on line 12, run the program, print out x. It is in fact 15. Okay, so no biggie here. Okay, so now we'll go ahead and implement the program in assembly. So we'll go ahead and we'll do a CP. I'm going to do a little shortcut here. I'm going to copy the previous one, which is 12, to this new one because they share a lot of code. So namely, sum. Okay, so that's the same. So we copy that to test.ttp-asm, and then we'll go ahead and change this ttp-asm over here. All right, so sum is all implemented, same way as before, nothing new, okay? We don't need Johnny, we don't need Ryan, so from line 35 all the way to line 51, we don't need. So 35 to 51, delete, okay? And now we're in sum, we don't have Ryan or Johnny anymore, so that means line 38 all the way to line 50 can be gone, so 38 to 50, they're gone. And instead, we have a local variable this time. So we do have a local variable, which is u int 8 underscore t. We call it x. And then we have x equals to 6 to begin with. Okay, so we're going to have to implement that. And, there's to do over here. So this is where I usually use a bookmark, like a to do to remind myself if there's stuff to be done here. So we'll go ahead and deal with the first thing first. So now we need a label, okay, main underscore x, which is my local variable. It's going to be 0. Main underscore LVS is going to be main underscore x1 plus, okay, because that's the number of bytes that I need for all my local variables. It's just 1. And also at the same time, at the entry point of the function, I have to allocate for the local variables. Okay, because no one, the caller cannot allocate for the local variables because the caller does not know how many bytes you need for the local variables. So the allocation of the local variables would be the responsibility of the function that is being called. Yes. Mm, say that one more time. Well, this time, but I can. It's not zero. It's LVS stands for local variable size. We do have a local variable x this time. The sum function is different because the sum function does not have local variables. Aha. Mm-hmm. So LVS is local variable size. So this time I do have to allocate for the local variables. So I'm going to do a LDIB with main LVS. We subtract that much from the stack pointer for allocation. And then whenever I allocate, I automatically go to the end to deallocate. Because if I don't do this right away, I will forget. And having a stack that is not balanced is the quickest way to lose track of the program. It's like, what just happened here? Why is it doing this strange thing? Because it's using the wrong location for the return address. Okay, so that's the most common way for a program to quote unquote crash and not do what it is supposed to. All right. So by the time we get to, we don't have Johnny and Ryan anymore. So instead we have x plus what, 1 here, or is it 2 first? I cannot remember which way. Is it one first? I think it's one first. Okay. All right. So are we still good at this point? We just added the local variable stuff. Okay. Allocate the stack space, deallocate the stack space for the local variable, and then we just have to figure out how do we push x plus one on the stack and how do we push x plus one on the stack at this point, right? We good? Okay. So the first thing most people do is to go like, oh, that's easy. How about just this? Nope, that's not going to work because x is, okay, so you go like, okay, this is not working because x is doesn't exist. We have main x instead. Okay, so we have main underscore x. It's still not working because this is not uh, suffix, or this is not a postfix notation. This is an infix notation. So you fix that. It looks like it's going to work, but it's not going to load the correct value on the stack. Because what it is doing is it's looking at the offset from where the stack pointer points to get to x, and then just add one to it, which is another address. And that particular address is not even something that you should be accessing, okay? Because it's the return address. So you don't need to push the address of the return address on the stack at any time. Okay? So you guys go like, I don't think so. I think this is going to be the right thing to do because the assembler, I mean the editor does not seem to indicate there's a problem. Well, let's put a halt instruction here and see what happens, right? Okay. So we go back to the stack, what it looks like, and we're gonna make a new one. So we'll go ahead and just duplicate this sheet over here to sheet number 2. And then in sheet number 2, we still have the return address to the entry code. That's still there. This location is supposed to be pre-allocated for local variable x of main. That's what it's supposed to be, right? And after we do this allocation, register D is going to be pointing to this location, and the other ones are still not used any at this point because they're below where the stack pointer points to. So this would be the picture at a halt instruction. Main underscore x is 0, which means adding 1 to it is going to be the address of the return address, which is location, which is FF or 255. So that's what I'm expecting the program to do at this point. It is erroneous, but I do want to show you why it is erroneous and what we actually ended up putting into register A. All right, so with that said, I'm going to switch back here, make sure the program is saved, because one of my favorite mistake to make is not to save the program before trying to run it. And then we go to test.ttp ASM, And then we just have to say, okay, what happens at the halt instruction? There we go. We get back here, go to the assembler, and then we go to the trace. Okay, we're already in the analysis tab, by the way. All right. So what was the last time we changed register A? Why is this not what I think it should be? Did I trace the wrong code? No, no, that's the right code. And this is test. Mm, this is the halt instruction on line 46. So by the time we get to line 46, okay, this is okay. And register A is a 0, 1. Oh, that is correct because we haven't added the stack pointer to it yet. So it is 1. That is correct. Okay. Hmm? Oh, because I forgot that I have to add the stack pointer to it to get to the address. So right now it just has the offset from where the add what this it has the offset from where the stack pointer points to. Well, regardless, this is the wrong thing to push on the stack, right? Because we are supposed to push the value of x on the stack, but we haven't really put a value into x yet. Okay, so that's probably the first thing we should do. Because what I'm trying to say is this one is not done yet. X equals to 6 is not done yet. So this is the first thing we also need to do. So we take this out, we just kind of slap it right here because that's what we need to do before we try to call sum. So here we have the usual code, okay, main x, add ad, put register b to be the 6, st a b. All right. So with this done, location 254 should have a value of 6. Okay, because you're back to the picture of the stack. This location should now be initialized to a value of 6. So we'll double check and make sure that really is the case. And that means go back to my prompt here, rerun the code. So without this tool, rerunning the code is going to take you a lot of time. Okay, so you really kind of want to consider getting Reverse Spider running as soon as possible because that will end up saving you a lot of time. So now we go back to the assembler and then we check out the write to location FE. And I think I might have made a mistake of not saving it first. Now, how do I know whether I did that or not? Control G in Vim will tell you whether the file has been saved. It says modified, which means I modified without saving it. Hmm? It's the percentage of your cursor relative to the whole file. Yep. Yep. We're going to do again. This time we should see location FE being updated to 6 because that's the initialization of local variable x of main. And scroll down. Yep, that's what we see. Excellent. So, getting back to the code, we need to push x plus 2 first on the stack. So we now know that this code is no good. Okay, it's not that easy. So that means the first thing we need to do is to retrieve the value of x and then we add 2 to it. That means, oh, okay, so that means we can just repeat the code that we had before. This is the address. LDAA. This will give me the value of x. So if we are not sure, we'll go ahead and test run the code again. So this time, by the time we get to the halt instruction on line 53, we should have register A having a value of 6, which is the value of local variable x. So we will run it again and see whether it is getting this done. All right. So we just keep going and oh, okay, that's correct. Okay, register A does have a value of 6. Great. We have to add 2 and then push it on the stack. So now we go back here and then we go like, okay, so we just have to add 2 to it. Okay, we LDI B into 2 into register B, add B to A, or increment twice, that it will do the same thing if you want to kind of save a little bit of code space. Increment A, increment A. So at this time, the halt, by the time we get to the halt instruction, register A should have 6 plus 2, which is an 8, right? Okay, we'll double check. Okay, we'll double check again. Okay, because it's so easy to run the code again, might as well do it. So this part is the easy part. Okay, the second part is the part to go like, what is it's not working? And then I will talk about how to use the trace to figure out why it is not working. Okay, so this is the easy part. We are just kind of practicing how to use the tool. We go like, oh, okay, great. By the time we get to the halt instruction, register A does have a value of 8, which is what we need to push on the stack. Are we good? Okay, so let's do that. Okay, so we'll go back here and then just go back here and then go like, okay, let's push register A on the stack, which is really just a decrement D, stda. Okay, so now we can push x plus 1 on the stack. So most of you are now thinking, hey, if we know how to push x plus 2, we know how to push x plus 1. Okay, so we're going to copy the code. So I'm not optimizing. Okay, I'm not saying, okay, we just need to push the value that is 1 less than register A has, but instead I'm going to go like, okay, let's be safe and not do any optimization. So we are going to copy line 5 to line 53 to the current spot over here, and then we push that on the stack. So decrement D, stda. All right, so we're going to double check this code that we just wrote, which is from line 59 all the way to line 65. Okay, we go like, okay, it looks the same as before. We are loading the offset from the where the stack pointer points to local variable x into register A. Then we add the stack pointer to register A. So now we have the address of X. And then we dereference the address of X so that we have the value of X. We increment it once, so we get to X plus 1. Then we push it on the stack. Okay, everything looks good, except it doesn't work. It doesn't work. We keep the halt instruction here, and then we'll see what happens. Okay, so we go. Oh, okay. We have to save the file. Okay, save, and then we run the code again. And it will start to figure out what was actually pushed this time on the stack. So I'm showing you all these modes of failure because in some of the programs that you'll be writing, these will be the most common modes of failure. So I'm trying to save you some time. All right. So we get to the halt instruction first. Okay, here's the halt instruction. And then we ask, what was pushed on the stack? Wait, it's supposed to be a 7, not a 9, right? So now what do? You execute a program backwards. Sorry? Hmm? Sorry? I'm supposed to increment. That is correct. Okay. But assuming that we don't know that ahead of time, right? So how do we debug the program? We know this is wrong. Okay. We know this is the wrong value. So that means whatever put a value into register A was wrong, which is this one here. But increment A is not that bad of a problem, right? Because all it does is to say, okay, if register A had the value of X, this would be correct. But we can now know that before increment A already had the wrong value. So who put 08 into register A to begin with, in the previous instruction? It was the LDAA instruction. So if the LDAA instruction is not giving me the correct value of register of local variable x, which is supposed to be 6, right? So where did it get this 8, right? So where it got the 8 is from location FD. So now you go to location FD and ask what is supposed to be at location FD. So according to this, we haven't put anything into location FD yet, or have we? So this is no longer up to date. This is no longer up to date because we pushed x plus 2 on the stack already. That is what the 8 is. And by the time we did that, the stack pointer is no longer pointing to where it used to be. It is now pointing to 1 byte below where it's supposed to be. That was the source of the problem. Okay, let me ask the question again. Okay, do we understand why we are grabbing the wrong result? Okay, if we go back to the assembler, because this is not the address of local variable x. According to this diagram, local variable x of main is supposed to be at location FE, but according to the trace, we went to location FD to grab the content to put back into register A. So now the question is, okay, we know FD is wrong, but why is it wrong? So it is wrong because the stack pointer is no longer pointing at the base of the frame. The base of the frame is referring to the first byte of the frame. The first byte of the frame is this byte over here. But the stack pointer, after pushing the second argument to main to sum, is already 1 byte below. That was the problem. Okay, so how do we fix the problem? You can increment the pointer, but there's an easier one to do it. There's an easier way to do it. The easier way to do it is simply to say all the offsets are now 1 byte off, and you adjust the offset instead. So the 1 plus is adjusting for the decrement on line 56. Because because everything is supposed to be referencing from the base of the frame, but because the stack pointer is now pointing to 1 byte below the base of the frame, we have to say, okay, all the offsets are now wrong. They're off by 1 byte. Is that okay? So now we can run the code again and see if we get the correct value this time. Make sure we save, and then we run it again. So this is a really kind of tricky thing, because as you push arguments on the stack, you have to remember how many bytes is the stack pointer pointing below the base of the frame. So once again, the frame would be all the local variables, the return address, and all the parameters. That forms the frame of one function call. So now we go back to the trace, and this time we push 7 on the stack. That's the right thing on the stack. Are we good so far? The rest of the program is easy. The rest of the program is not any different from the other one. So we can finish up the rest of the program, take out the halt instruction. We just did the to do, okay? So now we have the two arguments pushed on the stack. When we come back, we clean up the stack, then we can store the return value back to where x is, okay? So that means we just need to recalculate the address, LDI B with main X. I cannot use register A. Why not? Yep, because register A has the return value. I cannot overwrite it. So this store instruction on line 76 will change the local variable X, which is at location FE, from a 6 to an 8. Okay, so we'll double check. Okay, we'll run this code again. So if I was using GitHub, I would have done multiple check-ins already. How many people know how to use GitHub, what GitHub is? Okay. Okay. So you might want to look into it. It is free, right? So it's It's also one of the things that employers will look for is, do you know what is GitHub? If your answer is no, that pretty much ends the interview right there. I'm not kidding you. Okay, if you don't know what is GitHub in an interview for a job, for like a real job, for internship, not as bad. Okay, because they can probably teach you how to use GitHub or what is revision control. That's the name of that kind of a software. But in a real job interview, and the answer is no, I don't know what is GitHub. That pretty much ends the interview right there. They will give you the they will give you the bell. Ding. Next. Yep. All right, so we can double check, and we are in fact storing a 15 into location FE, which is the address of main x, which is the address of local variable x of main, which is at location FE. And I also have to double check everything, making sure that we do end up with the halt instruction where it's supposed to go, and the stack pointer is balanced, which means it goes back to 0, 0. All right, so that's pretty much the end of today's lecture. Do we have any questions about today's lecture? It's more or less a rehash of Monday's lecture, except with this little trick here, which is if you push anything on the stack, you just change the offset to everything in the frame. And once again, what is the frame? The frame will be everything that are your local variables, the return address, and all the parameters. That forms the frame of a function call. Yep. You don't want to mess around with the stack pointer. So don't do anything to register D. You can do something with the other registers, but not register D. Because register D is a stack pointer, it keeps track of which portion of the stack is actually in use. So you don't want to change that. Now, in the code that we have, okay, let me go back to the code. So instead of doing something like this, you could do something like this, and then you increment register A instead. That would be okay, but you don't want to mess around with the stack pointer itself. Okay, but personally, I prefer this because this is more runtime efficient compared to the other approach. Okay, now since we do have 2 more minutes, I'm going to explain why you don't want to increment the stack pointer, because the stack pointer is a fence. So think of this as a fence that stops gremlins from messing around with your stuff. So you ask, what is a gremlin? Okay, you go for Google search. Okay, Halloween is around the corner, so I think it is appropriate for this class. So gremlin, this is a gremlin. When it's nice and cute and orderly, this is what happens when you feed it after midnight. Okay, so just imagine that you have a fence that stops all the gremlins from messing around with your stuff. Okay, that fence is your stack pointer. Anything below where the stack pointer points to is outside of the fence. Anything that is above where the stack pointer points to is protected. Okay, so the question is, what do you want to do when you want to push something on the stack? You move the fence first. Okay, so that portion of space is now protected from the gremlins, and then you put your valuable stuff over there because now it is protected. Okay, so unless you are sure that whatever that location is not needed anymore, you don't shrink your fence. Incrementing the stack pointer is shrinking the fence. So you don't mess around with your stack pointer unless you're 100% sure that the whatever portion of space the fence is moved over is not needed anymore. Okay? And then someone is going to say, so, but computers don't really have gremlins, so what are you talking about? I am talking about interrupts, okay? Hardware interrupts, which is a concept that we don't have to deal with yet, at this point. But the point is, you don't change the fence unless you are sure whatever is getting exposed by moving the fence is not needed anymore. We good so far? Okay. So what you said was correct. It's okay. but because of the gremlins, we cannot do it. Yep. Yep. Oh. Oh, okay, gotcha. Okay, interesting. So it's basically some remnant of moving the fence. Even though you moved the fence back, the content was still there. Okay. Ah, I see. I see. Okay. Well, this is a movie recommendation for Halloween. It's alrighty. So let's get back to your lab today. So are you still out of your thing? Can you reset it? Hmm. Okay. We'll deal with that later. So today's lab is params and return value, which is something that we've been cooking since Monday. So by the time we get to this one, it should not be too bad. All right, today is October 29th. So we'll set the time to 1:20 p.m. And the access code is what the frame, WT frame, WT frame, all lowercase. And then we're gonna change the due date to October 29th, 1:20 p.m. There we go. Save and publish. You should be able to get to it now. And once again, the access code is all lowercase WTF RAM rain. Hmm? That's awkward one according to most people. All right, so I'm gonna stop the recorder and upload the video.